What's good? What's good? So, jumping right into PyTorch neural networks. Let's get into it. Welcome. In this lesson, you'll learn about neural networks using the PyTorch library. Starting from scratch, you'll learn how the neural network training process works, the role of activation functions, loss functions, and optimization algorithms, the concepts behind loss functions like mean squared error, and optimization algorithms like gradient descent, how to evaluate a neural network's performance, how to build neural networks for regression problems. Along the way, you'll use PyTorch to build, train, and test your own neural network for predicting rent prices from a street-easy dataset. Who is this course for? This course assumes no prior experience with, let me just put that. So this course assumes no prior experience with neural networks. We also cover the algorithms conceptually, so there's no need to understand calculus or linear algebra before taking this course. However, we do recommend having a basic working knowledge of Python, NumPy, and Pandas for data science before taking this course. We will review the basics of machine learning as we go, but we recommend having a basic understanding of machine learning concepts like supervised, unsupervised learning, and train test splits to get the most out of this course. We're so excited to see what you build. Here we see a feed-forward neural network with an input layer, updates the weights, then there's a hidden layer, again it updates the weights to a second hidden layer, and then an output layer measures the error, feeds it forward. Intro to tensors. Tensors are the fundamental building blocks of neural networks in PyTorch. Similar to NumPy arrays, tensors act as storage containers for numerical data. Most of the time, our data starts out in NumPy arrays or Pandas data frames. In order to use the data in PyTorch, we have to convert these data types to tensors using PyTorch's torch.tensor method. The torch.tensor method takes two arguments: the numerical data, NumPy array, Python list, or Python numeric variable, the desired data type, the dtype parameter. Common data types include torch.int for integers and torch.float for floats. Throughout this lesson, we'll be trying to build a neural network to predict the rent of an apartment. The dataset we'll be using was produced by StreetEasy for our original Intro to Machine Learning course. Here's an example of how we could convert a single apartment's rent to an integer tensor. So define the apartment's rent equals 2550. Convert to an integer tensor, rent tensor equals torch.tensor, rent, dtype equals torch.int. Now let's create a tensor that includes more information about our apartment, rent, size square feet, and age. Create a NumPy array with the rent in US dollars, size in square feet, and age in years. So apartment array equals np.array, a list with 2,550, 750, 3.5. Convert to a tensor of floats. Apartment tensor equals torch.tensor, apartment array, dtype equals torch.float. Often our data will start out as a Pandas data frame. In this case, we need to use the .values attribute of the data frame to retrieve the data as a NumPy array. Convert a data frame named df to a PyTorch tensor. Torch.tensor, df.values, dtype equals torch.float. Note that working with individuals columns of a data frame can occasionally cause problems due to dimension assumptions in Torch. One solution is to make sure the individual column is actually a full data frame by using two brackets to select it. So torch.tensor, df, a list, column, .values, dtype equals torch.float. Another is to use Torch's .view -1 method to automatically adjust dimensions. So you could do torch.tensor, df, column, .values, dtype equals torch.float, .view -1. Before working with tensors, let's practice running Jupyter Notebook cells and testing code on Codecademy. We've loaded a Jupyter Notebook in the workspace. Okay, this checkpoint is code cells, so to complete the checkpoint, select the code cell containing 3 import statements, click run, and then click save, click test work. Create a tensor containing the values 2,507 with the torch int data type. Assign your tensor to the variable apartment tensor. So what we want is we want to create a apartment array. It's a NumPy array with this list 2,500, or no, sorry, 2,507. And then we want to convert that to a tensor using torch.tensor. These are apartment array, and the data type equals torch float signage tensor. Don't forget to run the code cell. Torch int. My apologies. In this checkpoints code cell, can I just ignore that? I don't know, it's less distracting if I just have one set of instructions to look at. In this checkpoints code cell, we've already added code to create a data frame named apartments.df, or apartments.df, sorry. This array includes data on rent, size, and age of the apartments in our data set. Use torch.tensor to convert this data frame to a tensor with torch.float32 as the data type. Assign the result to the variable apartments tensor. Add your solution to the code, your solution here. So we have apartments.df equals pd.readcsv, streeteasy.csv. Select the rent, size, and age columns. Apartments.df equals apartments.df, rent, size, square foot, building, age, years. Okay, so now we just need to do torch.tensor apartments.df and dtype is torch.float32. Does that look right compared to the examples given? We want to convert the whole data frame, so we actually need dot values. Often our data are, in this case, we need to use dot values attribute to retrieve the data as an NumPy array. Looking good. Save it, test the work. Linear regression review. During this lesson, we'll be creating a neural network to predict the rent of an apartment based on features like square footage. This is an example of a regression problem in machine learning, a problem where we are trying to predict a target numeric value. In any regression model, we start with certain input features. Using those input features, we try to predict the target or output, sometimes called a label, although this is more common in classification problems. For example, we might try to build a model with input feature, square footage of an apartment, and target predicted cost to rent the apartment. Linear regression. The most basic kind of regression is linear regression. If you've never encountered linear regression before, we will do a quick review in this exercise, but it may be worth checking out our Intro to Machine Learning course. Linear regression models use linear equations to make predictions. The most basic linear equation is the standard equation of a line, y equals mx plus b. For example, here's a linear equation that uses square footage to predict rent. Rent equals 2.5 size square foot plus 1,000. This model claims that if we take the square footage of an apartment, multiply it by 2.5 and add 1,000, we will get the apartment rent as output. For example, if we're looking at an apartment with 500 square feet, we would predict rent equals 2.5 times 500 plus 1,000 equals 2,250. When talking about linear equations, we tend to use words like slope and intercept. In the world of machine learning, and particularly neural networks, we'll use slightly different language. Rent is the output or target. Size in square foot is the input feature. 2.5 is the weight associated to size square foot, and 1,000 is the bias. Models will often have more than one input feature. For example, we might be able to improve a model of rent costs by including the age of the apartment building. To include our age in our model, we just need to add age as an input feature together with its own weight. Here's a concrete example. Note that the weight associated to age is negative 1.5 with the negative sign included. In general, any linear model consists of some number of input features. Each input feature is multiplied by its own weight, creating a weighted input feature. All the weighted input features are added together with the bias. While the neural network models we will build in this course go beyond linear regression, many of these ideas, like inputs, weights, and biases, are present in even the most advanced neural network models. Suppose we're modeling the cost of rent using the linear equation, rent equals 3 size square foot plus 500. Use the code cell in this checkpoint to calculate the predicted rent for a 500 square foot apartment. Assign your answer to the variable predicted rent. So predicted rent was 3 times 500 plus 500. Suppose we are modeling the cost of rent using the multiple linear equation, rent equals 3 size square feet plus 10 bedrooms plus 250. What is the weight associated with the input feature bedrooms? Assign your answer to the variable bedroom weight. Suppose we are modeling the cost of rent using the multiple linear equation. What is the bias in this model? Linear regression with perceptrons. In the previous exercise, we used the following linear equation to predict rent costs based on square footage and building age. Rent equals 2.5 square feet minus 1.5 age plus 1,000. Our first step toward building neural networks is to transform this equation into a neural network structure called a perceptron, which has an input layer of the size square feet, the age, and 1 for 1,000, and an output layer. A perceptron is a type of network structure consisting of nodes, circles in the diagram, connected to each other by edges, arrows in the diagram. The nodes appear in vertical layers connected from left to right. What makes a network a perceptron is that it has one set of input nodes leading to a single output node. So what makes a network a perceptron is that it has one set of input nodes leading to a single output node. Let's walk through how this perceptron represents the original equation. Suppose we want to predict the rent price for a 10-year-old apartment with 500 square footage. First, we send each input value, 500 for square feet and 10 for age, into the input nodes. So the input layer is output layer. Then each input value flows forward into the edges and is multiplied by the corresponding weight. So I see. Lastly, the weighted values flow into the output node and are added together. This final equation is exactly the same as what we got with our original linear equation. Note that eventually we'll stop thinking of the biases coming from its own input node 1 with the weight 1000. This is helpful to see how these networks can exactly duplicate linear equations, but once we start working with PyTorch, the biases will simply be tacked on to the sum of the real inputs. Instructions: first, run through the Python code in the example cell. So let's use Python to perform the computation. We have size, square feet, the age, the bias. The inputs flow through the edges, receiving weights. So weighted size equals the weights, got you. The output node adds the weighted inputs, so weighted sum equals weighted size plus weighted age plus weighted bias, and we generate a prediction. It's the weighted sum. Let's add an additional input feature, bedrooms, to our linear regression perceptron, which corresponds to the number of bedrooms in the apartment. Here's a new network containing bedrooms. This new network has a weight of 3 for the size square feet, a weight of negative 2.3 for the age input, a weight of 100 for the bedrooms input, and a weight of 500 for the bias. Using this updated network, predict the rent for an apartment with size square feet equals 1250, age equals 15, number of bedrooms equals 2.0. Save the predicted rent price to the variable weighted sum. So define the inputs. sorry, not bias. They call it weighted size. Looks good to me. Oh, except, oh no, no. Looks good, looks good. Activation functions. In the last exercise, the output of the perceptron was a linear equation. If we stopped developing neural networks here, they would just be fancy ways of doing linear regression, but they are so much more. One of the ways neural networks move beyond linear regression is by incorporating nonlinear activation functions. These functions allow a neural network to model linear relationships within a dataset, which are very common and cannot be modeled with linear regression. Let's return to our perceptron from the last exercise. So this input layer, age, so bias, the output node produces a rent prediction in a two-step process. 1. Receive the weighted inputs. 2. Add them up. The result of this process is a linear equation. Activation functions take the linear equation as input and modify it to introduce nonlinearity. So again, activation functions take a linear equation as input and modify it to introduce nonlinearity. The process with an activation function is receive the weighted inputs, add them up to produce the same linear equation as before, apply an activation function. ReLU activation function. One of the most common activation functions used in neural networks is called ReLU. If a number is negative, ReLU returns 0. If a number is positive, ReLU returns the number with no changes. For example, ReLU -1, the output is 0 since -1 is negative. ReLU 0.5, output is 0.5 since it's not negative. If the weighted inputs coming into a ReLU node are 3 and -4, the output would be calculated by receiving the weighted inputs 3 and -4, adding them together, 3 minus 4 equals -1, applying ReLU, ReLU -1 equals 0, output 0. It might feel a bit strange that we're just turning negative numbers into 0, but this actually helps networks model datasets by having different sets of nodes be active or non-zero for different inputs. This is one of the reasons neural networks were originally thought to model the human brain, where different sets of neurons fire under different circumstances. Although, as we discussed, current evidence suggests neural networks don't really behave like the human brain. Zeroing out negative numbers also helps when training neural networks using gradient descent, which we'll discuss later in this course. Other activation functions. There are many other activation functions used in different neural network applications. For example, the sigmoid activation function only outputs values between 0 and 1 and is common in classification problems. We'll often use icons to indicate the activation function in diagrams based on the shape of the activation function when plotted. So ReLU is that sort of V-ish shape. Sigmoid is that sort of S shape. No activation function, just the weighted sum, is a plus. Don't worry too much about learning all the activation functions. As we cover different applications of neural networks, we'll learn about the standard activation functions of the for those networks. Calculate ReLU -3, ReLU 0, ReLU 3. Suppose the weighted inputs to a node are -3.5 and 3. Compute the output of the node in two ways. Linear output, no activation. Compute the output of the node using no activation function. Assign your answer to the variable linear output. So it would be -0.5. ReLU activation. Use the ReLU function we've defined for you to compute the output of the node. Assign your answer to the variable ReLU output. So define a function called ReLU. I thought. Confused. Oh. Suppose the weighted inputs to a node are -2, 1, and 0.5. We've tried to calculate the ReLU output in the code, in the cell below, but we've made an error. Can you fix it? The correct output is 0. Don't forget to run the cell and save the notebook before selecting test work. See the Jupyter help toggle at the top of the notebook for more details. So fix your solution. I know asterisk is asterisk args. Can we do that and then just wrap it all in this? I don't know if this is gonna work. I think it actually probably won't work, but I know there's a way to do this. You let it take any number of arguments. Oh no. Mm-hmm. I see. So it actually gave me a wrong answer, but that's on me for not explaining the problem the correct way. The way to do it would be you wrap x in sum. That's cool. What way would they have had me do it? I don't know. I want to see how they did it. ReLU x. Oh, so you just add. Okay, I guess that's a simpler way. Multi-layer networks. 6 minutes. So far, our networks have all had one input layer, one output layer. Activation functions help introduce nonlinearity, but to really model arbitrarily complex data sets, we need a more complex multi-layer network structure. We also need to train the network on our data so it can learn the complex relationships within the data set. Hidden layers. Hidden layers are layers of nodes introduced between the input and output layer. Here's an example of a neural network with 2 hidden layers. So the input layer, a hidden ReLU layer, another hidden ReLU layer, and then the linear output layer. Input data flows through the network from the input layer to the hidden layers and onto the output. Hidden layer nodes behave somewhat like output nodes have so far, receiving inputs and computing outputs. In other words, each node of the hidden layer functions like a perceptron. To be precise, each node in a hidden layer receives weighted inputs from the nodes in the prior layer, adds up all those weighted inputs with a bias term, optionally applies an activation function to the weighted sum, sends the result to every node in the next layer. Generally speaking, every node in a particular hidden layer will apply the same activation function. From now on, we'll stop creating a separate bias node. While helpful as an initial model, it will be easier to just remember that every weighted sum also includes a bias term. The training process. The training process has roughly 4 steps. Forward pass, feed forward. We feed input data through the network from layer to layer and calculate the final output value. Loss. We measure how close or far the network's predictions are to actual values. Backward pass/backpropagation. We apply an optimization algorithm to go back and update the weights and biases of the network to try to improve the network's performance, and then iterate. We repeat this process over and over, checking each time if the loss or error is going down. We included a detailed walkthrough of the feed-forward and trading process in the learning environment. When you're ready to start implementing this in PyTorch, select Next. So the input features are fed into the input layer of the network. The input values flow to the hidden layer. Each input is multiplied by a weight, and each hidden layer node adds up the weighted inputs. The hidden layer applies the ReLU activation function to the weighted sum. Each node in the first hidden layer sends the output of ReLU to the next hidden layer. These values are multiplied by weights and added together by each node of the second hidden layer. Each node in the second hidden layer applies the sigmoid activation function to the weighted sums. The outputs of the second hidden layer flow to the output node, each multiplied by a new weight. The output node sums up all of the weighted inputs it receives from the second hidden layer with no activation function. The output of the network is compared to the actual target value, and the error is computed, called the loss. Based on the error, an optimizer algorithm is used to perform a backwards pass, going back through the network to update the weights and biases. The process is repeated with new weights and biases. Over time, as the network learns, the loss error should decrease. Build a sequential neural network. Now that we know the basic structure of a neural network, let's build one in PyTorch using PyTorch's sequential container. Suppose we want to create the following neural network. Input layer, hidden ReLU layer, linear output. The network has input layer, 2 nodes, 1 hidden layer, 3 nodes with ReLU activation, 1 output layer, 1 node. We can build this network using 2 PyTorch methods inside NN sequential. NN linear for defining the layers and performing the linear calculations, weighted inputs plus bias, and NN ReLU for applying the activation function. Here's how we build the example network. So model equals NN sequential, NN linear, NN ReLU, NN linear. Cool. Let's go through this step by step. NN linear 2,3 connects the 2 input nodes to the 3 hidden nodes using our standard weights and bias linear calculation. NN ReLU applies the ReLU activation function to that linear computation. NN linear 3,1 connects the ReLU output from the 3 hidden nodes to the 1 output node, again using our usual linear calculation. Note that the connections between layers must be properly aligned. Once we have defined NN linear 2,3 as the first layer, the next NN linear must start with 3 nodes. Initially, each instance of NN linear will use randomly generated weights and biases. In the training process, which we'll cover later, the neural network will update these to improve its predictions. Running feed-forward. The first step of neural network training and predicting is the feed-forward process. To run through the feed-forward process with our sequential model, we need to pass a tensor as input to model. Typically, our input tensors will be 2-dimensional, consisting of rows, individual examples, in our case each row is an apartment, and columns, individual features. In our case, each column is an apartment property like size. Note that statisticians call examples observations. Suppose the 2 input nodes in our model correspond to building age and number of bedrooms. Let's create an input tensor with a couple apartments and run the feed-forward process. Note that typically input tensors are stored in a variable named x. This is a convention from mathematics that machine learning engineers follow. The input tensor is usually capitalized x and not little x to indicate that it is a 2-dimensional matrix of rows and columns. So create an apartments equals a NumPy array with 103, so 100 years old, 3 bedrooms, and 54, so 50 years old, 4 bedrooms. Convert to a tensor. X equals torch.tensor, apartments, dtype equals torch.float. Run feed forward. Model x, output the result of a feed forward through the network layers is a tensor. We use the tensor method and it outputs a tensor with negative 23.0715 and negative 11.8710. Grad function, so gradient function, add backward 0. We can interpret this output by associating each row of output to the same row of the tensor input. Input row 103 corresponds to the output prediction of negative 23.0715. Input row 50 and 4 corresponds to output prediction of negative 11.8710. Of course, as predictions, these make no sense, though we'd love to have negative rent, but we haven't trained this model at all, so that isn't surprising. We'll discuss the last piece of this output, grad fn equals add mm backward 0, when we start training models with backpropagation. Use NN sequential to create a neural network model. So we're going to use NN sequential to create a neural network model with an input layer of 3 nodes, hidden layer of 8 nodes with a ReLU activation function, output layer 1 node. Assign your network to the variable model. Because NN sequential will randomly initialize weights and biases, we've set a random seed in every checkpoint code cell. This is generally a good practice. That means the initial weights and biases are the same every time we run the same code. Do not edit the seed value 42, as that is needed for our testing code. So create a model. We do NN dot sequential, NN dot linear 2 3, NN dot ReLU, NN dot linear 3 1. Sorry. Name torch is not defined. Oh, I need to run this. Checkpoint 2 3. Recreate the model. Wait, did I test the work? Not quite. We're not finding the right. Oh, yeah, because I copied it. So we need 3 nodes, 8 hidden layer nodes, recreate the model from the prior checkpoint. This time add a second hidden layer with 4 nodes and a neural network sigmoid as the activation function. Don't forget to run the cell and save the notebook before selecting test work. So, and that's sequential. This time add a second hidden layer with 4 nodes. So 3 input features, 8 outputs, and ReLU. And in that sigmoid. I'm a little bit confused. Oh, it says 4 nodes. Got you. That makes more sense now. Recreate the model from the prior checkpoint. This time add a second hidden layer with 4 nodes and an NN sigmoid as the activation function. Don't forget to run the cell and save the notebook before selecting test work. Open the Jupyter help toggle. So I guess you need another linear between these. So when I just add the sigmoid, it tells me that there should be 3 instances of NN linear, 1 of NN ReLU, 1 of NN sigmoid. So where should the third NN linear go? That's what I thought. Oh. First, follow the instructions to run the dataset import. So let's create a model and feed forward all of our real StreetEasy data. First, run the next code cell to import the StreetEasy data and convert the size square feet, bedrooms, and building age years columns into a PyTorch tensor. We'll use these 3 columns to try to predict rent. So load the pandas data frame, apartments df equals pd.readcsv, StreetEasy CSV, create a numpy array of the numeric columns, apartments numpy equals apartments df, size square foot, bedrooms, building age and years, dot values, convert to an input tensor, x equals torch.tensor, apartments numpy, dtype equals torch.float32, preview the first 5 apartments. So again, let's create a model and feed forward all of our real StreetEasy data. First, run the next code cell to import the StreetEasy data and convert it the size, square foot, bedrooms, and building age. I think there's something I forgot to run, huh? Building a neural network class. Hold on 1 second. Build a neural network class. While NN.sequential is pretty useful for creating neural networks, often AI developers need to create non-sequential types of neural networks using object-oriented programming. Using object-oriented programming gives developers much more control over neural networks. With sequential, we can only feed data from one layer to the next. Building in logic to skip certain layers or to loop others can improve neural network performance. For that, we need the flexibility of object-oriented programming. In this exercise, we're assuming no familiarity with object-oriented programming. Don't worry if the syntax isn't completely familiar or clear for now. Our goal for now is to help you navigate object-oriented programming, neural network code, and prepare for more advanced courses. Let's start by building a familiar sequential network with object-oriented programming. Create the NN regression class. In the prior exercise, we created sequential neural networks using this syntax. Model equals NN.sequential with the inputs. In the syntax, NN.sequential refers to a type of neural network, sequential neural network. Types of things in object-oriented programming are called classes. The variable model is a specific sequential neural network called an instance of the class, we can create our own classes or types of PyTorch neural networks using the syntax class nn underscore regression nn dot module. So coming in here, initialize the network components. Inside the class declaration, we need to initialize all the layers and activation functions we plan to use. We can think of this step as gathering all of the ingredients for a recipe. We're initializing all the layers and activation functions we plan to use. Note that the self syntax just allows us to reference these variables like self.layer1 in the next section of defining the class. Define the forward pass. Now that we've gathered the ingredients, we need to describe how to combine them in order to perform the feed forward operation. We'll create a forward method that dictates the flow of how an input data tensor X is passed from layer to layer through the network. Within this method, we can use all the ingredients we already gathered, like self.layer1 and self.relu. Def forward self X, define the forward pass, X equals self.layer1 X, X equals self.relu X, X equals self.layer2 X, X equals self.relu X, and so on. Here the syntax X equals self.layer1 X, for example, takes the input tensor X and passes it through the input layer to the next hidden layer, and that's it. We now have a new type of PyTorch neural network called NN regression. Instantiate the model. What we've created so far is just a type of neural network, just like we had to call model equals nn.sequential to create an instance of the sequential class. We'll need to run model equals nn regression to create an instance of an nn regression neural network. So in the checkpoint 1 code cell, we've included code to create the nn regression class. So we've included code to create the nn regression class from the narrative, create an input tensor of apartment data, feed forward to make predictions. Run the cell. The output from this network should be the same as the sequential network from the last exercise. Once again, this network is completely untrained, so it isn't surprising that the predictions are very bad. Note, even though you haven't written any code in the cell, still save and select test work to move on. Don't forget to run the cell and save the notebook. So we have this manual random seed. We create this class, the nn regression class. So nn regression is extending nn.module. Our constructor just takes in self, super nn regression self.init. I think I'm trying to remember what super does again. I think it allows it to be globally defined. Kind of want to, they might tell me later, or they might not. So I'm just gonna, I might find this out later anyway, but I'm just gonna ask. In the provided code, super is used to call the constructor of the parent class, which is nn module in this case. The call to super nn regression self.dunder_init within the init method of nn regression class is essential for properly initializing an instance of the nn regression class, which inherits from nn module. Nn module is a base class for all neural network modules in PyTorch. It provides basic functionality for all derived classes, such as keeping track of the neural network layers and providing methods that are essential for training, such as parameter management and support for moving the models to GPU. By calling super.dunder_init, you ensure that the nn regression class has all the initialization that nn module provides. This includes setting up the model so that it can automatically track all of its layers, parameters, and submodules. It enables the nn regression class to use all methods and properties from nn.module. This is crucial for defining custom neural networks in PyTorch, as it allows for seamless integration with the broader PyTorch ecosystem, including the ability to easily define forward passes, compute gradients, and update weights. In simpler terms, super in this context is ensuring that your custom neural network class nn regression is properly set up by leveraging the initialization process defined in PyTorch's base nn modules class. Cool. So we ran this, and then we've created a new neural network class called onehidden with a 2-node input layer, a 4-node hidden layer, a 1-node output layer. This class does not yet have any instructions or feed forward. Try running the cell without making any changes to the code Without any linear layers or activation functions, the input tensor should be output as is. In the forward method, define a feed forward that takes the input x and feeds it through. So feeds it through self.layer1, self.relu, self.layer2. Run the cell again to see the new predictions. Okay, so just going back here, trying to get a better understanding. So we have this layer 1 is this first linear layer. Layer 2 is another linear layer. So we go from 3 to 16, 16 to 8, 8 to 4, and 4 to 1. Initialize activation function, so self.relu equals relu. And then our feed forward pass is, so it takes in the input, and we run it through layer 1, run it through our relu, run it through layer 2, run it through another relu, run it through layer 3, run it through another relu, and then run it through layer 4, and then we return our x. Okay, cool. And all we have to do is we input a tensor as our x. It's tensor of the numerical features, size square foot, bedrooms, and building engineers from our apartment's data frame. Get the values and make them floats. Cool. And this is essentially doing like .head. So in here, class 1 hidden, def init self, super 1 hidden self .init. So we initialize the layers. We have a linear layer with 2 inputs and 4 outputs, and a linear layer with 4 inputs and 1 output, and then a relu. Our forward pass, we have to write that. So in the forward method, define a feed forward that takes the input x and feeds it through. So def self forward, and similarly to here, x equals self layer 1, right? Just making sure. Okay. Let's look at one way defining classes can be helpful. We've included the same 1 hidden class from checkpoint 2 in the checkpoint 3 code cell below, but we've updated the line def init to have another input, def init self num hidden nodes. This input num hidden nodes determines the number of hidden nodes in the hidden layer. For example, within the init method, the line self.layer1 equals nn.linear2 num hidden nodes uses num hidden nodes to define the connections between the input and hidden layer. Below your solution here, add the input 4 to the line model equals 1 hidden. And run the cell. The output should be the same as for checkpoint 2, where we hand coded the value 4 for the hidden layer. Now change the number of nodes in the hidden layer to 10 and run the cell again. How does the output change? Save the notebook after running with 10 hidden layer nodes and test your work. Pretty cool, right? This is just scratching the surface of the power of defining our own neural network classes, but in the next exercise, we'll return to the problem of actually improving our predictions by training sequential neural networks. The loss function. In the last 2 exercises, we predicted the rent of some apartments by feeding them through neural networks. The networks were untrained, so the predictions weren't very good. Let's start improving those predictions. To make better predictions, we first need to know how bad our current predictions are and how to track improvement as we train our model. This is the role of the loss function. The loss function is a mathematical formula used to measure the error, also known as loss values, between the model predictions and the actual target values, sometimes called labels, the model is trying to predict. Difference. Suppose we run a neural network on an apartment with $1,000 per month rent, but the network predicts $500 per month. The simplest way to measure the loss in this case is to calculate the difference. 500 minus 1,000 equals negative 500. The difference indicates that the prediction was $500 below the actual rent. For just one data point, the difference seems reasonable, but imagine we have a second apartment with rent $1,500, but the model overestimates the rent as $2,000. The difference in this case is 2,000 minus 1,500 equals 500. With one loss of 500 and another of negative 500, the average loss for the model is actually 0, but that doesn't make sense since this network isn't perfectly accurate. The problem is that the negative loss canceled out the positive loss. To fix this, we need to force the difference to always be positive, mean squared error. One of the most common loss functions is mean squared error, MSE. Mean squared error makes differences positive by squaring them. To calculate mean squared error on our two example apartments, we would calculate the differences, 500 and negative 500, square both, take the average, so 500 minus 1,000 squared plus 1,500 minus 1,000 squared over 2 equals 250,000. A loss of 250,000 seems very high, but remember that we've squared all the individual differences. To help interpret MSE, we'll sometimes take the square root of the MSE, so the square root of 250,000 is 500. An average loss of 500 makes a lot of sense in this case. MSE and PyTorch. PyTorch has already implemented most of the common loss functions. To use PyTorch's implementation of MSE, we'd run loss equals nn.mse loss. Now that we've instantiated loss, we can compute the mean squared error by passing two inputs, the predicted values, the actual target values. Just as we use X to stand for input features in a neural network, it is common in machine learning to use the variable Y to stand for the target values. In this case, our target isn't two-dimensional, so we use lowercase y. Let's calculate MSE for two example apartments. Predictions equals torch.tensor, 500, 2000, dtype equals torch.float, y equals torch.tensor, 1000, 1500, dtype equals torch.float, print loss, predictions, and y. Choosing a loss function. The loss function plays a key role in training, so it is important to select the right one. Sometimes it is worth experimenting with a few different loss functions to see how each behaves. For example, the squaring process in mean squared error emphasizes the largest differences between predicted and target values. Sometimes this is helpful, but in other cases it can lead to overfitting. In those cases, instead of squaring differences, we might choose to take the absolute value to produce positive values. This is called the mean absolute error. Suppose we fed two apartments through a neural network with the result predictions 750 and 1000, targets the actual rent 1000 and 900. We've tried to calculate mean squared error below, but we've made a mistake. Can you fix our calculation? So difference 1 is 750 minus 1000, difference 2, so that minus that, difference 2 is that minus that, mean squared error equals difference 1 plus difference 2 over 2, show output MSE. So in exercise 7, we built the neural network. Model equals nn.sequential, nn.linear, nn ReLU, linear ReLU, linear ReLU, 316, 16, 8, 8, 4, 4, 1. When we fed our apartment data forward through the network, the first 5 predictions were these. The first 5 targets, the actual rent values, were these. Use PyTorch's nn.mse loss function to compute the mean squared error of these 5 apartments. Assign the result to the variable mean squared error. Don't forget to run the cell and save the notebook before selecting test work. So what we need to do, these are our predictions, this is our target, and what we need to do is use PyTorch's nn mean squared error loss. boolean value of tensor with more than one value is ambiguous. Oh, I see. And MSE loss predictions y. Let's try restarting the kernel. Look at me. Oh yeah, I gotta be right. It's gotta be the computer. But let's try it. Because I'm confused. Okay, so it's me. I'm the issue. So, and then MSE loss. Predictions and y. That's MSE. I guess what we could do to just make it look exactly the same. Will this work? No. So make it look exactly the same as the example. And then we could do MSE. Interesting. So cool, it worked though. Save it and test the work. Let's make the result from checkpoint 2 a bit more interpretable. No, not quite. Pass the predictions and targets. So it wants me to do it like that. Let's make the result from checkpoint 2 a bit more interpretable. Compute the square root of the mean squared error tensor from checkpoint 2, hint variable to the 1/2 power. We'll compute the square root of a tensor assigned to variable, assign the result to the variable RMSE. This stands for root mean squared error. Okay, so we need the square root of our MSE tensor. Is it just MSE? Looks right to me. Looks like this model's error for rent in dollars is around 62,000. We can improve this quite a bit in training. The optimizer. With a loss function, we can tell how well or poorly our neural network is performing. To improve on our model's performance, we need to adjust the weights and biases. This is what the optimizer algorithm does. Gradient descent optimization. There are many different optimization algorithms. One of the most common is called gradient descent. Imagine we're on top of a mountain and our loss function tells us how high up we are. Our goal is to get down the mountain, making the loss function as small as possible. Unfortunately, it's a dark night, so even with perfect sight, we couldn't see very far. Suppose using sight or some kind of radar, we can determine how the mountain slopes around us for about a meter in any direction. With only that information, we might pick where the mountain slopes down the most and move in that direction. We don't want to move too far at once because the mountain slope might change as we move, so we'll only move a short distance in our chosen direction before pausing and reevaluating which direction goes downhill the most. This strategy is essentially how gradient descent works. It uses calculus to determine the gradients of the loss function. These gradients are the direction signs that indicate which way to adjust the weights and biases in order to decrease the loss function. Learning rate. How far to move at each step is called the learning rate. Choosing a learning rate involves some trade-offs. A learning rate too high may cause the model to move too quickly and miss the lowest point. A learning rate too small may cause the model to learn slowly or get stuck. The learning rate is a classic example of what we call hyperparameters, values tuned and tweaked by machine learning engineers during training to improve performance of the model. The process of adjusting hyperparameters in search of the best model performance is called hyperparameter tuning, using optimizers in PyTorch. A popular optimizer in PyTorch called Atom uses gradient descent with a few extra bells and whistles, like adjusting the learning rate dynamically during training. To use Atom, we'll use the syntax import torch.optim as optim, optimizer equals optim.atom, model.parameters, LR equals 0.01. Model.parameters tells Atom what our current weights and biases are. LR equals 0.01 tells Atom to set the learning rate to 0.01. To supply Atom to a neural network, we need to perform the first backward pass, calculate the gradients of the loss function. These determine the downward direction. And 2, step, use the gradients to update the weights and biases. The syntax is to compute the loss, so MSE equals loss predictions y, backward pass to determine downward direction, MSE.backward. Apply the optimizer to update weights and biases, optimizer.step. Note that backward is applied to the computed loss, not the loss function. This is why the output of the loss function includes the parameter grad fn MSE loss backward 0. This parameter is the function used to perform the backwards pass. 1. Import PyTorch's optimizers using the alias optim. We've defined a sequential neural network model already in the checkpoint 2 code cell. Initialize the Atom optimizer using model's parameters and a learning rate set to 0.01. So optimizer equals optim.atom model.parameters LR equals 0.001. We've already defined a neural network, run a forward pass with some of our apartment data, and computed the loss from that forward pass. Add your solution here, add code to initialize Atom in the variable optimizer with a learning rate of 0.01. So again, optim.atom model.parameters LR equals 0.201. Okay. Use the loss we've already assigned to MSE to perform the backwards pass. MSE.backward. Use optimizer to update the weights and biases. Oh. So the initial loss is, what's that, 29 million. And after optimization, the loss is 29 million, and sub about 8,000 or 80,000. No, that's about 8,000. Training. In the last exercise, we optimized weights and biases using the following code. Predictions equals model X, that's the forward pass. MSE equals loss. Predictions Y, we computed the loss. MSE.backward computes the gradients. Optimizer.step updates weights and biases. In this exercise, we'll turn this code into a training loop that will perform multiple optimizations in a row, attempting to decrease the loss as much as possible. The only additional line of code we'll need inside the loop is optimizer.zeroGrad. This line resets the gradients for each iteration. The gradients determine the direction to move the weights and biases, and we want to pick a brand new direction each time. Here's an example loop. Note that in neural networks, iterations of the training loop are called epochs. Num epochs equals 1000 for epoch in range num epochs. Predictions equals model X, forward pass. MSE equals loss, predictions Y, compute the loss. MSE.backward, compute gradients. Optimizer.step, update weights and biases. Optimizer.zeroGrad, reset the gradients for the next iteration. And again, we're turning this code into a training loop that will perform multiple optimizations in a row, attempting to decrease the loss as much as possible. The only additional line of code we'll need inside the loop is this optimizer.zeroGrad. This line resets the gradients for each iteration. The gradients determine the direction to move the weights and biases, and we want to pick a brand new direction each time. Here's an example loop. Note that in neural networks, iterations of the training loop are called epochs. We also want to print out the loss value regularly during training to track the improvement of our model. Here's one example of how to print out the epoch number and loss every 100 epochs. If epoch plus 1 modulo 100 is equal to 0, print format epoch plus 1 divided by number of epochs, mean squared error loss, MSE.item. Note that since epoch starts at 0, the 100th epoch occurs at epoch equals 99. So the line if epoch plus 1 modulo 100 is equal to 0 checks if the current epoch is the 100th, 200th, and so on. We call .item on MSE to print out only the loss value. If we just called MSE on its own, we'd also print out the grad fn. First, run the setup and import data cells in the checkpoint 1 code. So run this import, importing this apartments data frame from the StreetEasy CSV. We're choosing the numerical features, creating a tensor from the numerical features of apartments df, all with a type of torch.float, and we create the tensor for the targets. So we use just the rent from apartments df, and type float, view -1 to make sure we're recognizing that we just need this one column. Alternatively, we could have put this in those, but we're not going to do that. So we've created a neural network to find a loss function and initialize an optimizer already. Note on the network, since we now have 14 input features, we've increased the size of our hidden layers to try to capture that complexity. But we are still following a common neural network architecture where the first hidden layer has twice as many nodes, 128, as the next, 64. We've also tried to write a training loop to train our neural network for 500 epochs, but we've made a mistake. As a result, our loss values are extremely high. Can you spot our error and fix the training loop? Okay, so set the random seed, define the model equals nn sequential with a linear layer, 14, 128, ArrayLu, another linear layer, 128, 64, another ArrayLu, and then a final linear layer, 64 to 1. Our mean squared error loss function plus our optimizer, so loss equals nn.mean squared error loss, optimizer equals optim.atom, model.parameters, and our learning rate. Our solution, our num epochs is 500 for epoch and range num epochs. Predictions equals model X, MSE equals loss, predictions Y, MSE backward, optimizer.step, don't modify, keep track of the loss during training. If epoch plus 1 modulo 100 is equal to 0, print f epoch plus 1 divided by num epochs. Mean squared error loss is our MSE.item. And again, there's an error that we need to fix in the training loop. So we haven't reset the gradients. pretty cool. Now, using the same model setup, we've written another training loop. This time we've made a different mistake and the loss values don't seem to be changing from epoch to epoch. Can you fix our mistake? So num epochs 500 for epoch and range. Num epochs predictions equals model X. MSE equals loss predictions Y. MSE dot backward for backward propagation. And then save it and test the work. We've already defined a neural network loss function in Optimizer. Fill in a training loop that will train the neural network model for 1000 epochs. Do the additional epochs improve the model performance? So num epochs is 1000 for epoch and range num epochs. Set the mean squared error. So mean squared error. Oh no, actually set the loss. Loss equals NN. Oh no, we already have that. So MSE equals loss predictions. We haven't set predictions in Y. How does it go again? So predictions equals model X. I see. So first we'll make predictions. I'll put that over there. Then we compute the mean squared error. Misspelled that. And then we do the backward propagation. And then we do our optimizer step. And then optimizer.zero grade. Oh, did I do that? Oh no, that's fine. Predict. Cool. Significantly better. Testing and evaluation. In the last exercise, we ran training loops that decreased the loss from our neural network, but decreasing the loss during training only tells us that the model is becoming more accurate on the data it is learning from. We also need to evaluate the model on new data, save the best model for future use. Instead of waiting to collect a new data set, machine learning engineers usually only train models on a portion of the original data set, called the training data, and then evaluate it on the remainder, called the testing data. This process is called the train-test split. We'll use the Python library scikit-learn to perform this split. The syntax is from sklearn.model selection, import train-test split, xtrain, xtest, ytrain, ytest equals train-test split, x, y, train size equals 0.80, test size equals 0.20, random state equals 2, where x contains all of our input features, y contains the targets we're trying to predict, train size equals 0.8, tells scikit-learn to use 80% of the data for training, test size equals 0.2, Tell scikit-learn to use the remaining 20% for testing. Random state equals 2 sets a random state so that we create the same train test split each time we run our code. This produces 2 sets of data. Data for training the model, xtrain, input features, and ytrain, corresponding targets. Data for testing the model, xtest, input features, and ytest, corresponding targets. Evaluation. To evaluate our model on new data, we will use our testing data with the following syntax. Model.eval with torch.nograd, predictions equals model, xtest, test MSE equals loss, predictions ytest. So again, model.eval with torch.nograd, predictions equals model, xtest. So we pass our test set to the model to make predictions, and then we test the mean squared error with our loss from the predictions and the ytest. Got you. Where model.eval sets the model to evaluation mode with torch.nograd, turns off gradient calculations, which we don't need outside of training. Otherwise, this code is basically the same as code we used in training. We run feed forward to predict the targets for the test data set. We compute the mean squared error loss between those predicted targets and the actual targets, saving and loading models. Once we have an incredible rent prediction model, we want to be able to save and load models without going through the entire process. Again, the syntax is save the neural network to a specified path. So torch.save, model, model.path, load the saved neural network from the specified path, loaded model equals torch.load, model path. In the import data cell, we created 2 tensors. So first, let's run this. X contains our numeric features, our input features, and Y contains the corresponding target rent values. Use scikit-learn to split these into training and testing. So use scikit-learn to split these into training and testing data sets. The training data set, xtrain and ytrain, should have 70% of the data. The testing data set, xtest and ytest, should have 30% of the data. Use a random state of 2. Hold on 1 second, sorry. So we're going to do, we already imported from, no we didn't. Okay, so from sklearn.model selection, import, train, test, split, xtrain, xtest, ytrain, ytest equals train, test, split, x, y, train size equals 0.70 in our case, and our test size 0.30, and our random state will be 2. We've already defined a neural network in training loop, but we forgot to only train on our training data set. Can you fix the code so that the neural network is only seeing the training data during the training process? So random seed, set up the model, mean squared error, loss, and set up our optimizer, and then we're predictions with model x train, and compare those predictions to our y train. Save the model from checkpoint 2 to the file model.path, and that is torch.save model.path. We've saved a model trained for 20,000 epochs in the path model20k.path. Load this model to the variable loaded model and evaluates performance on the test dataset. So torch.load model 20k dot path, and to evaluate it, test mse dot item. Within the evaluation, so model.eval switches the model to evaluation mode with torch.nograd. Make sure we're not updating the gradients on each pass. Our predictions are making predictions using the X test, and test MSE equals loss predictions Y test. Model is not defined. Test MSE. Okay. What's the discrepancy? So torch.save model. Did I run that? I did. It's torch load. Oh, loaded model. Loaded model. On average, our model still has error probably larger than we'd want, but for a quite small neural network without any tuning, this is pretty good. Visualization, run the cell below to plot our model's predictions against the actual targets for the test data set. If our model was perfect, all the dots would be on the dashed line. How do you think we've done? It's pretty good. Pretty good. Review. Congratulations on finishing this lesson. You've taken a huge first step in your neural network's journey. Just in this lesson, you've built and trained a neural network from end to end. More specifically, you've turned linear equations into perceptron models, learned about loss functions, activation functions, and optimizers, built sequential neural networks, built neural network classes using object-oriented programming, trained and evaluated a neural network for predicting rent. We've created an open-ended Jupyter notebook for this exercise. Practice everything you learned by building your own neural network from scratch, following the outline in the notebook. We won't be checking your work. So that's cool. But I'm treating this as a refresher. So what we're going to do is review. This is a project. When building a neural network class using object-oriented programming, what is the difference between the init and forward methods? The init method feeds the data into the The init method gathers the different ingredients of the neural network. Select layers and activation functions. The forward method defines the order in which the input data flows through the network. The init method defines the backward pass, so it's this. Fill in the code to create a training loop with 1,000 epochs using a neural network stored in model. So num epochs equals 1,000 for epoch in range num epochs. First we make predictions. Then we calculate the mean squared error. Then we do a backward pass. Mean squared error dot backward, and then we make a step. Suppose a soccer team develops the following linear model to connect shots in a game to actual goals scored. Goals equals 0.1 times shots plus 1. Drag and drop the question answers. The target is goals. The input feature is shots. The weight of shots is 0.1. The bias is 1. A node in a neural network receives the following data. Sum of weighted input is 3. Bias is negative 3.5. If the node uses ReLU activation, what value does the node output to the next layer? 0. When computing the mean squared error, why do we square the differences? Squaring makes all differences positive so that negative and positive differences don't cancel each other out. Fill in the blanks to compute the mean squared error loss between a model's predictions and the actual target values y. So import torch.nn as nn, loss equals nn.msc loss, and then loss predictions y. Fill in the code to convert the NumPy array to a PyTorch tensor. So import NumPy as np, import torch, np array equals np.array 1.5, 2, and 30. Tensor equals torch.tensor, np array, dtype, torch float. Looks right to me. What are the advantages and drawbacks of using object-oriented programming to define a neural network compared to NN sequential? Using NN sequential is much more straightforward. However, using object-oriented programming gives the machine learning engineer more flexibility and control over how the data flows through the network. Use PyTorch's NN sequential method to build the following neural network. From torch import NN, model equals NN.sequential, linear is 2 and 3. This is a hidden ReLU layer, so NN ReLU, and then linear 3 to 2, and another ReLU. Cool. Imagine that we've run the following code to create a test train split. From sklearn.model selection, import train test split, x train, x test, y train, y test, train test split, x, y, train size equals 80, test size equals 20, random state equals 2. Fill in the code below to train and then evaluate a neural network stored in model. So loss equals nn MSE loss, optimizer equals optim.atom, model.parameters, LR equals 0.001, num epochs equals 1000, for epoch and range num epochs, predictions equals model x train, MSE equals loss predictions, y train, MSE.backward, optimizer.step, optimizer.zeroGrad, keep track of the loss, set evaluation mode, model.eval, turn off gradients and test, with torch.nograd, predictions equals model x test, test MSE equals loss, predictions, y test, and we're good. What does the learning rate parameter control in gradient descent? The learning rate is a measurement of the efficiency of the optimization algorithm. Essentially, it measures how effective the optimization algorithm is. No. How far the weights and biases are updated in each iteration of training? Yes. Yes. Drag the steps of the neural network training process in order. So first we do a forward pass, then forward pass, calculate loss, backward pass, iterate. Feeling good, feeling great. Next steps. Next steps, what's next? Congratulations on completing Intro to PyTorch and Neural Networks. In this course, you learned about creating neural networks with PyTorch and are now able to build neural networks in PyTorch, define activation and loss functions, evaluate neural network performance, create real-world predictive models. Now that you finish your course, you may be asking what's next. Here are recommendations for next steps. So we could learn PyTorch for classification, learn more about PyTorch. This course takes the next step in the neural network journey, covering classification models, where we try to predict categorical results instead of numeric results. We could do Intro to AI transformers, use PyTorch and Hugging Face's libraries to fine-tune transformers. Or we could learn intermediate Python 3 based off of my time. Let's see, because I want to do Intro to AI transformers. I don't want to skip classification, but I only have a limited amount of time. So let me just check my schedule. Okay. Yeah, I'm already over budget really, but I mean, screw it, right? Let's go. Welcome. In this lesson, you'll learn the following topics. What are transformers? Traditional count-based versus large language models. A brief history of transformers. How do transformers work? You know what? No, time will move on me very quickly. I've fine-tuned before. I can do this after. Right now, I need to be efficient with my time. And so I'm going to be regimented with myself here and move on to because I need to do a refresher on SQL. So I'm going to do that in a separate stream. I know, but next time. Peace.